Welcome to the finalization of our Zero Energy Design course. I hope you have learned a lot and enjoyed yourselves on the way towards this final week of the MOOC. Tess and I have studied the final submissions of plans, and in this last lecture I will discuss 6 of them from 4 different climates. The first case is from Luca, who lives in London, UK, which has a temperate climate. London's temperate climate is characterized by cold winters and relatively cool summers, although you know now that this is changing and that cities in themselves are warmer due to the urban heat island effect. Only 38% of all hours can be made comfortable by means of passive design measures alone, so technical help is needed here. Here you see Luca's house, which he shares with 5 other dwellers, a semi-detached Edwardian house, which uses almost 3,800 cubic meters of gas for heating, hot water and cooking. In addition, the house uses almost 8,200 kilowatt hours of electricity for lighting and all sorts of appliances. Taking into account the efficiency of power plants, the primary energy use is approximately 18,000 kilowatt hours. So the total demand is 45,000 kilowatt hours, or 55,000 kilowatt hours in primary energy. Luca later mentions 49,000 kilowatt hours, but I could not find where that figure comes from exactly. Anyhow, to me it seems a very high demand for energy, but let's see. Here you see the energy measures Luca proposed to reduce the energy demand. Thermal insulation in roof and floor, a conservatory and solar light tubes. And these are the measures proposed to reuse residual energy. A heat exchanger to recover heat from the shower and a tank to preserve hot water. Other measures are also possible, but practically a bit more difficult. In total, the reduce and reuse steps led to 51% of savings on the original demand, which is good. Luca calculated that with the PV panels he wants to install on the roof of the conservatory, he can produce 11,000 kilowatt hours, leaving a similar amount of energy still to be produced elsewhere. We however think that demand is somewhat lower due to our earlier calculation of the end-user demand. Nonetheless, with the measures currently proposed, it will not be possible to get to net zero energy. How can it be solved then? We think that thermal insulation on the facade will make a big difference, as well as energy-saving appliances, such as fridges. And perhaps in these urban settings, the municipality should take care of a district heating network supplied by a renewable source of heat. Not far from London, we will find Henk, who lives in Delft, quite close to where I'm standing right now actually. Delft in the Netherlands also has a temperate climate, very similar to London. Henk lives alone in an apartment block. His energy use is modest, as you can see here. To put it in perspective, we've compared his to that of Luca in London. You can find that comparison here. The total amount of energy used differs by a factor of 9, but per square meter Luca uses almost twice as much, and per person it is 50% more than Henk. Of course, Luca's house is older than Henk's, but still. Henk proposed several logical measures to reduce the demand of his apartment, as you can see here. And adding measures to reuse and produce energy, Henk gets to a net zero energy apartment block. He has also drawn a glass house over the galleries, which will act as an energy buffer. In his case, of course, he would need the full support of his landlord and fellow tenants. Well done. Now we continue to a different climate. Julia lives in Sofia, the capital of Bulgaria, a country largely experiencing a continental climate. The annual mean temperature is not much different from London and Delft, but the seasonal differences are huge. Nonetheless, passive measures could solve about 42% of comfort hours. Julia lives together with someone else in an apartment at the top of an urban block. Her system is all electric, using an air conditioner to both cool and heat, a not very efficient solution for which a heat pump system would make a big difference. Here you see the passive and active measures proposed by Julia. They seem logical to me. In climates like this, thermal insulation is very important, as well as admission or obstruction of sun, depending on the season. These are the measures to reuse waste heat from ventilated air. I will get back about the heat pump solution later. In Julia's case, 11.6 square meter of PV is sufficient to produce the remaining demand of electricity. This way, Julia managed to get to net zero energy demand over a year's time. Well done. We do have a question, however. In this overview, we see that the heat pump will also serve an underfloor heating system, replacing the air conditioner. A good solution, but where does the heat or cold come from? Heat from ventilated air is already used to heat up incoming air. To use it for heating too would be too much in a cold winter. Using outdoor air is possible, but this would make the efficiency of the heat pump very low, close to that of an air conditioner, hence a high electricity demand. This is because in freezing winter the heat pump cannot get much heat out of the air, and in hot summer there is little cooling capacity in the air either. So the best solution would be the soil, as this will have a stable temperature of around 12 degrees, but then of course Julia had best organize it with her fellow residents. Now, onwards to the tropical climate of Brazil, where another Julia lives in Goiânia. The mean temperature is high and actually on the average comfort level of humans in buildings. Therefore, 68% of comfort hours can be realized by means of passive measures. Julia's starting conditions can be found here. She has an all-electric house and an energy consumption close to that of an average Dutchman, but much less per person and per square meter. This is an overview of the measures proposed by Julia for the 3 steps of our approach. First, reduce. Insulation and double glazing is also useful in the tropics in order to keep the heat out, and avoiding upheating of course is paramount. And Julia proposes vegetation, night ventilation and a green roof to attain this. Julia also proposes to recover cool from air going out by ventilation, a good one, plus a compression cooler. And finally, 10 PV modules are required to fill the energy gap. 11 if Julia refrains from expensive reuse measures, which is fair enough. I will however get back to the performance of PV panels in the tropics later. But first let's have a look at another tropical destination, India, where Nikhil lives in Jaipur. Jaipur also has a tropical climate, but can get a bit hotter in summer and colder in winter than in Brazil. Nikhil uses 1,744 kilowatt-hours for cooking and 6,609 kilowatt-hours for electric purposes. He has no hot water in the kitchen. Here are Nikhil's reduce measures related to insulating the building envelope and reducing ventilation losses. Good measures, I think. Together, the reuse and the reduce interventions of Nikhil lead to around 70% of demand reduction. The remaining demand can be solved by PV panels. In his case, 10 kilowatt will generate an overproduction of around 3,500 kilowatt-hours. This could be used for electric vehicles. I could propose that. The lessons we can draw from the 2 topical examples discussed are the following. Passive measures are most effective in saving energy. In the tropics, heat or cold recovery is relatively expensive compared to the energy savings they accomplish. So leaving them out is possible if we can compensate that with extra electricity production from photovoltaics. But be aware, please use realistic values for PV production. The yield of PV in a tropical climate is not the best due to clouded or hazy skies, so don't use the maximum output of PV panels. Both Julia in Brazil and Nikhil in India used a production of 650 kilowatt-hours by one panel of 1.5 to 1.7 square meter. I'd rather use 200 to 300 kilowatt-hours maximum. Now, the final example of our students, and therefore we move to a place called Calexico in California. That used to be a nice band too, by the way. Karen lives in this desert climate. And here you see the starting conditions for Karen. The mean temperature is similar to that of Julia in Brazil, but for her the seasonal and diurnal differences can be really extreme, where they are very stable in the Amazon area. Karen's energy use is based on gas and electricity. Based on the values she mentioned at first, we calculated a total demand of 13,555 kilowatt-hours, but later Karen mentioned a value of about 86,000 kilowatt-hours, which is incredibly high, even when accounting for the primary energy used in inefficient power plants. I will get back to this later. By means of these measures, Karen manages to reduce the energy demand by 32%. In the desert climate, because of the great temperature differences, I would also try to apply thermal insulation as well, and mass, to preserve the pleasant mean temperature indoors. It was not for nothing that we saw ancient cave dwellings in the desert of the US. Karen also proposes heat recovery from shower water and from breathing windows, using outgoing air, cool during the day and warm during the night. For this to be optimal, the thermal insulation I mentioned is essential. There is also energy potential in her vicinity. As expected, the final demand is to be solved by PV, for which Karen uses 68 panels, each producing 657 kilowatt hours per year. In this case of a desert climate, the 300 watt peak and the output of more than 600 kilowatt hours per annum is acceptable. Her number of panels is based on the initial demand, later reduced by her measures. We think it's too high, perhaps based on the primary energy of electricity, and maybe the conversion factor of fuels to kilowatt hours need to be checked too. It might lead to less PV panels needed, which makes it all much cheaper. And this is Karen's clear overview of measures. Add thermal insulation and the demand gets even lower. So, this brings me to the end of this final lecture. I want to recapitulate a few lessons. You will have noticed that every climate can use the same approach to zero energy buildings, but that the solutions are often different. Passive measures fitting the climate are always suited, but reuse measures are more fitting climates with temperature differences. Also, PV can be used everywhere, but the orientation, the angle and output is different. Don't use the same figures everywhere. Stay sharp in your calculations when using data and conversions. We also saw that you, students, understand that the primary energy demand of a building is higher than its end use, but it does not mean that you have to solve the entire quantity of energy yourself. Your PV on the roof just has to generate your own end user demand, and not the inefficiency of a power plant you are not using anymore anyway. That makes life easier, doesn't it? Well, that's it. If you want to continue with our more professional Prof Ed online course, please keep an eye on that one, which will probably start early 2020. And now I really have to say goodbye. Thank you for joining this course. I hope it has helped you to design and redesign buildings to energy neutral, sustainable ones, which contributes to making the world a better place. Also on behalf of Eric and Tess, I wish you all the luck in the rest of your career and hope to meet you in the near future. Bye.